Hey, okay, so I wanted to go over a little bit about the quantitative graphs. And for this lesson, I'm going to use the PowerPoint that goes along with the textbook. You really do need to read the textbook in this class, and the PowerPoint is a great resource to point out the topics that are pretty important, and then you can go to the textbook for a little bit more detail. So definitely don't skip over the textbook and just ignore that and think that you're going to get the summary and that's enough. So we did some things with chapter 1.1, and now we're moving on to chapter 1.2 and 1.3 with quantitative graphs. And so I'm not going to go over all of these slides specifically because you will be able to go over them in detail yourself and looking at the textbook. I just want to point out some of the key points that I don't want you to miss. Okay, so a couple of things. First of all, a dot plot is one of the easiest graphs you can make, but it really only works with a very small set of data. So on your worksheet 1.2, you are asked to create a dot plot, and you want to make sure that you're always working with a set of data that ideally includes integer values or counting numbers. Not something that would be, say, 4.2, 4.3, or a continuous type of a variable. And so you also are going to just number basically a number line, and then a dot plot is exactly what it sounds like. You're basically just counting up the number of occurrences, in this case of 0. There's one occurrence of 0, and so you'll stack up the dots as you go. So click on this, it's off a little bit. So as I get 0, I get my 0 here, and then I would move on and say, okay, do all my ones. There's 1, 2, 3, 4, 5, 6, 7, 8. Oops, 8. And so I should have 8 dots here for the one part, right? And so every single title, no matter what it is, it always needs, every single graph always needs a title, no matter what type of graph it is. So in this case, they're labeling their axis down here with the units, so number of goals scored. And the title of this graph really is what is in the title of the table here, number of goals scored per game by the 2004 U.S. women's soccer team. When we describe a set of quantitative data, we always use the acronym SOX. I always use the acronym SOX. So you'll hear me say, don't forget your SOX. And what SOX stands for is shape. The O stands for outliers and gaps. C stands for center. And S stands for spread. And depending on what type of center you're using, whether that is going to be mean or median, that will determine what type of measurement you're going to use for spread, which would be standard deviation or IQR. And we have some other measures of spread too, but such as range. So you always want to describe the overall pattern of your data using SOX and make sure that you include the context. Because as you know, we discussed earlier that data without context, numbers without context are meaningless. So when you're describing your data set, you want to include all the components of SOX. And one of the components that's difficult for some students is describing the shape. So with shape, we use terms such as roughly symmetric, and that is if the data looks approximately the same on both sides. I didn't mean to cross that out. Here, let's fix that. Let's maybe use a highlighter instead. Roughly symmetric. And notice we're saying roughly. So roughly is a key word because no data in the real world is going to be perfectly symmetric. So down here we have a symmetric distribution. That means it's about the same on both sides. You remember cutting out like a Valentine heart by folding the paper in half and cutting the heart out and unfolding it. It looks the same on both sides. That's what we're talking about when we say symmetric. And of course it's symmetric usually about the center. If something is skewed, we need to say which direction it's skewed in. So is it skewed to the right or is it skewed to the left? So if it's skewed to the right, which is this one over here on toward the right, it's skewed in direction of the tail. And that's confusing for students. But basically, what that means is those outliers or those extraneous data points are pulling the mean and pulling the average toward it. And then this other one would be skewed to the left. Okay, so keep moving on that. Okay, comparing distributions. So in your notes, I have posted comparing words. So when you're asked to compare a distribution, you can't just list all the statistics for both data sets and assume that somebody can make a conclusion from that. You need to use comparing words such as more than, less than, the range is wider than, or more symmetric versus left skewed. You always want to discuss the shape, center spread, and possible outliers, but use comparing words. So you can't just say, say the mean of South Africa is this and the mean of the UK is that. You need to say the mean of South Africa is greater than the mean of the United Kingdom as far as household size. Again, don't forget your context. Okay, you definitely want to read in your textbook about how to make a stem plot. This is something that people have seen before usually, and usually are pretty good about reading a graph when they're given a stem plot, but when it comes to actually constructing a stem plot, people make a lot of mistakes. One of them is deciding what should be the stem and what should be the leaf. So the key is that the leaf has to be the final digit. You can't have 2 digits and say that that's a leaf. You may need to decide to round your data to, say, the 100th place or the 10th place so that all of your data is consistent, and then use that final digit as the leaf. And then you also need a key or a legend that goes along with your stem plot so that somebody can look at your graph and understand exactly what it means. So you can follow the directions in your textbook, and then I've also put additional notes there. On this stem plot that they're giving here as an example, you'll see that if we take the number 50, the way that works, the way that works, we have the number 50. What that means is that the tens digit is going to be the 5 and the 0 digit is the leaf, right? The tens digit is the 5, that's the stem, and the 0 digit is the ones place, that's the leaf. So we would have to have a key, which they're showing over here, 4 and then 9, indicating that 44 bar 9 would mean the number 49. So you'll notice here we have 5 and then the bar and then 2 zeros. Well, that's because 50 shows up twice in this data set. And so we need to make sure and include both of those. And if you notice, if you turn your head and look at a stem plot, it starts to resemble a histogram. So it's really easy to look at a stem plot and determine the shape as well as the tendencies of where your clusters are as far as your numbers go. Okay, so then you'll also see sometimes back-to-back stem plots. So these back-to-back stem plots are exactly that. So in this case, we have 2 categories, females and males. So we're breaking our data out by gender. And then the key will be the same. So we're still using this key of 4 bar 9 to represent 49, which is going this way for females. Let's see, we'll highlight that over here. So like the 49, the 49 shows up right here. So it's actually going to be backwards. It's mirrored because the stem, when you have back-to-back stem plots, will go right down the middle, and then your leaves will come off of either side. And so it's one way that we can compare 2 distributions. It's not my favorite way to compare 2 distributions. I would much prefer a box plot usually, But the thing is, about stem plots, we still get each individual data point. And so we can tell where there are gaps in our data. Oops. For example, right here in the ones place for males, we have a lot more gaps in our data for males than we do with females. For females, let me change colors over here. The only gap we have in the female set of data is right there. So we'll see in just a minute that with box plots, we lose all that ability to see the gaps in the specific data points. So a stem plot is useful. It's not my favorite, but it is useful in comparing data sets. Okay, next we have histograms. Histograms are super common. We're going to see a ton of those. So for histograms, you guys have a lot of practice working with histograms, but people also make several common mistakes. So I just want to highlight some of the few things to watch out for here. First of all, a histogram looks like a bar graph, but it's not. A histogram looks like a bar graph that is touching. All the bars should be touching each other unless there are actually gaps between the data classes. But a histogram is used for quantitative data, and a bar graph is used for categorical data. So with your histogram, you always want to make sure that you decide at the beginning what class width to use. And the easiest way to do that is to look at your minimum and your maximum value, and then try to determine how many bars you would like to have on your graph. And then that can help you identify the class width that you can use. You usually want to have your class width be something like easy to work with so that you can graph it on paper, like 0 to 10 or 0 to 20. So you'll notice on the worksheet 1.2 that I had you change the directions for creating the histogram for the text messages, because originally I told you guys to use a class width of 5, and you send way too many text messages to do that. So I changed it to do a class width of 10. So anyway, you always want to make sure that they are equal widths, and then you can make your histogram either using counts, which we call frequency, or relative frequency, which are percents. Either of those are fine. You just have to label your axes so we know what is going on. And so the height of the bar represents the count if you're using frequency, or the percent if you're using relative frequency. So again, the bar should touch unless that class actually does not contain any values at all. So your book walks you through making a histogram. There's also a document in OneNote that walks you through making a histogram. Just the way that we will label it, you don't actually write it like this, 0 to 5. You would just write 0 to 5 like that. But know that you can think of it, if you want to think of it with notation, think of it as including the lower boundary here and not including the upper boundary. So it's 0, including 0, and all the way up to anything that is just less than 5. And then we would, so you need to go look at the book page on 35 to get the actual data set, and you'll see where these numbers come from with the count. So when I'm creating my histogram, I want to have from 0 to 5, and the count is 20. So I'm going to draw my histogram just like that for the first one, and then from 5 to 10 goes up to 13, which is right about there. Oops. And then 10 to 15 is 9. My bars are a little bit crooked there. 15 to 20 is 5, so roughly there. 20 to 25, I have 2. And then 25 to 30, I have just 1. Let's see this. And then if I want to, I can go back and fill in my bars. So it just makes it a little bit easier to read and maybe cleans up my kind of crooked bars here. All right, and there's my histogram. And so which way is this skewed? Yep, to the right. So it's right skewed because it's being pulled in the direction of the tail. So what this graph is missing is a title. So we've labeled the y-axis over here, the number of states, and we've labeled the x-axis percent of foreign-born residents. Actually, the way that I did this is the count, but I believe the book shows it both ways. So when it copied this document, I'm sure it was showing how we're converting this from count to percent. But basically, I'm showing the count here of foreign-born residents, and then I would need a title that is also descriptive of the data set that I'm looking at. So if I did want to show this histogram with relative frequencies and percents like this, that would be fine. I just need to change my y-axis to show this to read percent of states, and then I would want to determine the percentage out of the total. So 20 out of 50, 13 out of 50, 9 out of 50, and so on. Okay, and then lastly, I just want to highlight a couple of things in the third section, 1.3, because that's really where we're calculating the statistics and the values that describe quantitative data. So if you want to switch to the 1.3 PowerPoint printout and follow along, you can do that. So the first thing is the mean. The mean, I think you know, just means the average. And the average is basically we're just adding up all of the observations and dividing by the number of observations. So if you look on the formula sheet, it gives you this what looks somewhat complicated formula, but really that's all you're doing. You're adding up all the observations and dividing by the number of observations. The notation is really important. So you want to remember that X bar, that's what we call that, X with a little bar over it, is the mean. Okay, and then moving on to the next one, the median is another way of describing center. So both the mean and the median describe the center. And the median, you'll remember from probably middle school, 9th grade, it's actually the midpoint of a distribution. So if you are to find the median, what you can do, what you can do is order all the numbers from smallest to largest, and then you're just going to count from the outside and the inside inward till you get to the middle. So if you have the number of observations is odd, then the median is actually the number that's right in the center of the list. If it's even, then you have to take the two numbers in the center of the list and average those together. Okay, so whether you use median or mean to describe your data really depends on what your data looks like. So if you are using a data set that is symmetric, we tend to use the mean. If you're using a data set that is skewed to the right or the left or has extreme outliers, we tend to use the median because we don't want our center to give false information. And the mean is not resistant to outliers, whereas the mean is resistant to outliers. So one way of thinking of that is talking about the average value of a variable, which is actually the mean, and the typical value, which would be more like the actual center of the distribution. Some people might even say the typical value is what we call the mode, which is the number that shows up most frequently. We don't use the mode very much in statistics, so just be careful what it's talking about in terms of the center. So the key is, though, when you're talking about the center, that's going to define which measure of spread you use. So if we're talking about the median, we really want to use the interquartile range to define the spread. And so if we use median for center, then we need to go with IQR for spread. And the IQR is really just finding the middle 50% of the data set. So we need to find the first quartile, which is 25%, the third quartile, top 25%, or the bottom 75%. And then just remember that the IQR is actually a number. It is not a range of numbers. It is a number, and you calculate that by finding the value that shows up at the third quartile minus the value that shows up at the first quartile, and that gives you your IQR. Okay, so, and this is a good example of it. Again, you can look at page 57. I won't go into all the detail here. And we will also talk about how to do this on the calculator in the next lesson. So outliers. So we need to know the IQR, what the IQR is in order to calculate outliers. So we call it the 1.5 times the IQR rule. That's a really nice descriptive name, but that's what it's called. And that's how we're going to find outliers. So outliers are any significant variations from the norm in a data set. And so the 1.5 times the IQR rule is just one of the rules we can use to find outliers, but it's the most common one. If you look on page 57 in your book, it will walk you through it. But basically what you're doing is you're finding the IQR first, and then anything that is 1.5 times that value above the third quartile or below the first quartile would be considered an outlier. So the lower boundary would be anything below negative 26.25. An upper boundary would be anything greater than 83.75. So in this data set that they're using as an example, 85 is the only outlier in that data set. Okay, then you'll also hear something called the 5-number summary. So this is kind of an important way of describing data. We use this with box plots a lot because actually you're using your 5-number summary to create a box plot. So the 5-number summary is simply these 5 different statistics. So the minimum, the first quartile, the median, the third quartile, and the maximum value. And so when we say, describe the 5-number summary, you need to know what that's comprised of. So you need to know that it's minimum, Q1, median, Q3, and maximum. And the calculator will give us that information. So I will show you how to do that in the calculator soon, not in this lesson. But we use the 5-number summary to create the box plots. And we really just call them box plots. We really don't use the term whisker plot, but some places do, and so you might see that term. If you go into the notes section, I have a very detailed note sheet about how to create a box plot and how to create side-by-side box plots, and so I'm not going to spend too much time on it here. And then the standard deviation, what you really want to understand is that the standard deviation is not resistant to outliers or skew, just like the mean. So when we use the mean, we will use the standard deviation for the measure of spread. The standard deviation is calculated using the mean, and that's why it can't be resistant to outliers. So I'm not going to dwell too much on the calculation here. This formula looks complicated. It's really not too bad. Whoops. It is on your formula sheet, and you'll see it's the S with the little x next to it, so sub x, and then this formula. And this is the sample standard deviation. And we'll talk about the difference between the population standard deviation and a sample deviation in a future lesson as well. Okay, so we already talked about choosing measures of center and spread, but you do want to pay attention to this. And just know that you can't just go by the summaries of the data set. So if, for example, you're given a 5-number summary, that's not enough to make a decision about your data. Again, you always want to use mean with standard deviation, median with interquartile range, and the big message here is that you always have to plot your data, because the data, as we learned from a graph, tells a story. We talked about that today. So the data, when it's plotted into a graph, it will tell you a story, and the trends and the patterns are much more visible from a graph than just a list of numbers, whether it's your data set by itself or your statistics that are describing those distributions. Okay, so that's it for 1.3. Definitely go back and read this chapter. You'll want to use it to complete your skinny, and we'll go from there. Thanks. Have a great day.